some SVM code and you just have to make minor tweaks. In some sense, this homework lets you play with an existing data set and almost similar, I mean a data set that you've already seen before, an idea that is very close to something that you've already used before, to see what these tiny changes in the learning objective does to your classifiers. And that's the experiment part. And of course, there's the theory part of the homework, which requires you to read a document that I have uploaded on the course webpage. And it should not be terribly hard. In some sense, the answer very closely resembles what's in that document.
So that's a bonus question?
Yes. There's a bonus question, yes, for the holidays. You are free not to do it. And the other thing is based on some rather impassioned emails that I got, thanks to those of you who sent it, I've decided to move the project deadline to the day after the exam. That doesn't mean that you have to wait till the day after the exam to submit it. You can submit it today if you want, or you can pretend that the deadline was never moved, get it done before the exams, or if you want, you can submit it on the day after the exams. And I've opened up the submission window on Canvas. There's a description of what is expected in your project report. Please do not set and write anything more than 6 pages. Take some pity on me. I have to read like 90 of them. And they're all, a large fraction of them are about something that I have very little understanding of, like something about cars. So it takes some time to understand and digest the applications, not so much the learning part. So take a look at what's in the requirements, and just if you've not started writing it, I encourage you to start writing it. I've typically found that writing takes longer than doing, at least for me, so please do that. Any questions about any of this? Yes?
Can I ask a question on the regularizer and the logistic regression?
Sure.
What does it mean? Like in the SVM, we were maximizing margin.
Right.
In this case, what do we...
So I am going to give you 2 answers to this question. So the question is, what does the regularizer mean in logistic regression? In SVM, there was this nice geometric intuition. So the first one is, in the regularizer, in the way we derived it in logistic regression, the regularizer is just a prior probability distribution over the weight vector. Remember what we did? We said the weights, each weight, so your weights consist of a weight vector, W1, W2, all the way to, let's say, Wt. You have a d-dimensional vector. The regularizer is derived by saying each of these weights, say W2 here, is drawn from a Gaussian centered at 0 and a certain standard deviation, a fixed standard deviation. What does this mean? It says, in the absence of any other information, if your data set is empty, W2 likes to be at 0. So you can interpret this as a push for sparsity. If you can think of it as, I just added that feature number 2, and that feature is irrelevant, so this regularizer pushes it towards 0, pushes the weight towards 0, thereby saying, yeah, the feature is not really relevant. That's one way of thinking about it. Another way of thinking about it, and this is a general way of thinking about regularizers are simply functions that express...
Was that dimensionality reduction when you're...
No, that doesn't do dimensionality reduction. This is very, very loosely feature selection. This does not reduce the dimension. The vector is
but
still...
It reduces the weight of the...
It reduces the importance of the feature. It effectively says the feature is irrelevant. Remember what we did this in Winnow, right? We said you can add arbitrary number of features. If a feature is irrelevant, the Winnow algorithm will pick up on it. This is the way logistic regression and SVMs pick up on irrelevant features. You can say that this is a way of feature selection in some sense, right? That's one. So those are the 2 different ways. One is I just have a some prior information about this weight vector, and I just believe that the weights should be centered around 0. The weight, you can think of the weight vector as a point in this d-dimensional space, right? And this regularizer simply says the distribution over these points is the highest. The probability of these points occurring at random is highest at the origin. That's one way. The other way of thinking about it is this feature selection. In the absence of any information, this lets you push for less complex models by selecting fewer features. And we know complexity is bad. Good question though. Any other questions about the homework, projects, regularizers or anything? Alright. There was also this thing about, there was a point about the video. On, I think one of the lectures we had to lose the video, or not lose, but we had to record it offline and then upload, and there's some confusion about the video. We'll figure it out and hopefully we'll send out an announcement by tomorrow. Alright, so if there are no questions, let's move on to a fun new section on neural networks. So this lecture is entirely by popular demand. Every year when I teach this class, I get like at least 10 students telling me, oh, why did you not teach a class on neural networks? So here's a lecture on neural networks. So let's just take stock of where we are before actually getting into neural networks. Through the semester, we've seen a whole bunch of learning algorithms. We started off with decision trees, we went to perceptron and Winnow, we went to AdaBoost, SVMs, naive Bayes, logistic regression, and across all of these learning algorithms, we actually, in fact, we looked at these learning algorithms through a bunch of general machine learning principles. We looked at the idea of overfitting, looked at mistake-bound learning, pack learning, and the general idea of sample complexity, hypothesis spaces, and the choice of the hypothesis space being driven by the VC dimension of the hypothesis space, the difference between training errors, and really the notion that generalization is the most important thing in learning. And we looked at this almost a recipe for creating learning algorithms in the form of regularized empirical risk minimization. We saw that this idea shows up even if you are Bayesian, for example. And we looked at Bayesian learning. Under Bayesian learning, we looked at maximum a posteriori and maximum likelihood learning. Okay? All of this is good, but most of these classifiers that we looked at are linear. Sure, you can get kernels into support vector machines, but some of you noted that I did not really talk about a learning algorithm with kernels. Effectively, all the learning algorithms we looked at produce linear classifiers except for decision trees. So there are at least two open questions. One, how do you train nonlinear classifiers or nonlinear regressors? And the second one is, where on earth do those features come from? And this is a problem that many of you are facing in your projects. You want to somehow invent features and it's not clear where those features come from. So let's look at some, hopefully we'll look at an answer for both these questions today. We'll look at what is a neural network and general algorithm for training neural networks. In some sense, this gives us a way to almost mechanize machine learning. We have a general algorithm for solving optimization, namely gradient-based methods, stochastic gradient descent. Which takes away the pressure of actually inventing algorithms from you. You just know, all you need to do is invent loss functions now. There are actually some decisions that you still have to make in stochastic gradient descent, and we'll see how we can get rid of some of them. And towards the end of the lecture, I'll wrap up with practical concerns about training neural networks. I should mention before I start, this is a ridiculously vast area. I'm not even touching the surface I'm barely touching the surface of this area. This is a very fast moving topic. You might have seen news articles about deep learning, deep neural networks and such things. Hopefully what I'm covering today will let you kind of make sense of some of those things. So let's start off with what's a neural network. In particular, look at what the hypothesis class is and what kinds of functions they express. We've seen linear threshold units. In some sense, this is all a big part of what we've seen in the semester. The way it works is you have some features. I'm calling them x1 through x4. You have 4-dimensional vectors. The 1 is always there because it's a biased feature. You take a dot product with some weights and you threshold it and you get an output. So you get a prediction which is simply the sign of the dot product, right? And no shock here because you're experts at this now. And we looked at many learning algorithms for this thing. We looked at perceptron, logistic regression, blah blah blah, and all of these roughly you can say minimize some loss function, possibly regularized. So the real question that is left unanswered here is where do those features come from? See, because if you knew what the features were, and if your concept was classifiable, was learnable under that feature space, any of these algorithms will work. You know, perceptron, we know that it stops making mistakes. Your data is linearly separable. SVMs will find you a linear classifier, logistic regression will work, any of these things will work. But that's a big if. Where do those features come from? One way of motivating a neural network is, what if those features were outputs of a classifier? So remember at the beginning, the first lecture I said, if you don't know how to predict something, you should think about trying to make it the output of a classifier. I don't know how to get these features. Maybe I can throw in a classifier. How does that work? Let's start off with our network. This is a network, right? Let's start off with the classifier that we have. You know, separate the inputs from the outputs, and let's look at the first case. Maybe you bring in another classifier, a different classifier that produces the first feature. Another linear threshold unit that produces the second feature, and so on. What we end up with is called a two-layer feed-forward network. Two layers because you have the hidden layer. You usually don't count the input as a layer. You have the hidden layer and the output layer. Earlier, everything that we saw before was a one-layer network, one-layer feed-forward network. It's called feed-forward because the arrows point in one direction. So the way to think about this kind of a network is that this middle hidden layer tries to learn a good, for some definition of good, it tries to learn a representation of the inputs so that the top layer can now classify them. So effectively we are going from just learning classifiers to also learning representations. The top one, like a very hot new conference for neural networks is actually called the International Conference for Learning Representations. Learning representations is probably one of the most fundamental questions that is frankly an open question in machine learning because it's not clear how to do it. So this is a proposal, this is one way of answering that question. I want to learn representations, I want to get a good representation, and I'm going to convert it into a learning problem. Questions before going ahead? Yes?
This seems really similar to ensemble methods. What's the, like AdaBoost, what's the...
In fact, it's interesting that you mentioned this. You can think of this as an ensemble of these, underlying classifiers. The big difference though is in how these things are trained. Typically, not always, but typically these neural networks are trained in an end-to-end fashion. In one shot, as a loss minimization, using loss minimization, you take your data set, you get a neural network. In AdaBoost kind of a thing, or in an ensemble, you have your weak classifiers could belong to a different family from the top level classifier. Here we are basically saying we are going to write down the entire thing as a mathematical function, as a single function. What's the function that we had for AdaBoost? It's not clear because it depends on your rules of thumb. And now the pressure is now moved to inventing these rules of thumb. We could have used decision trees, for example, but that there is some diversity in decisions there. Whereas here you're saying, yeah, I don't care about the internal thing, I'm just going to make everything an end-to-end, train everything in an end-to-end fashion. Other questions? Okay, so in this two-layer network, just a matter of terminology, this dot product followed by the threshold is often called a neuron. So this picture has 5 neurons. There are 4 hidden neurons and 1 output. Okay, this is just notation. Alright, but I really haven't solved the problem, have I? I just made the problem a little more difficult, but I haven't solved it. I still have to figure out where these x's come from. I don't know what the input features are. Maybe I don't want to think about the input features at all. What I'll do is I'll probably think of them as another outputs of other classifiers. So I can, separate out this part from the rest of it and introduce another set of neurons that produce a feature. And then you'll ask, okay, where do the inputs to those neurons come from? And by the way, that will give me a 3-layer network. I can add one more layer. I can keep adding layers, and that gives me a deep network. At some point, you probably feel tired and you stop. And when do you stop? The answer is often something like cross-validation. This is the depth of the network. The depth of the network is a design choice. Okay? Questions?
At each layer, do you have to use the same classifier, or could each neuron be a different?
Each neuron could be a different classifier. In this picture, I have just, this is just a cartoon picture. In fact, this is a cartoon in multiple ways, other than the fact that it was roughly sketched out. Notice that the input and the hidden network layer have the same number of neurons. Nothing prevents me from having 5 in the middle, or 200 in the middle, or only 1. If I have only 1 though, it's kind of useless, because it just is a single thing. So having 1 is no use, but having more than 1. To answer the question that you asked, yeah, sure. The nature of the internal neurons decides the hypothesis cluster. Was there another question?
So they're all feed-forward.
In this, yeah, they're all feed-forward. Yes. They take, yeah, we are considering what's called the forward pass in this case. Yes.
Did you simulate multiple layers by taking the outputs and feeding them back into the inputs of the?
So those are called, there you read. Yes and no. Yes, in the sense that they exist. No, because they are a beast to train. But that idea of taking the output and treating it as another input is very useful for what is called recurrent neural networks, where they are the input not of this particular time step, but at the next time step. So there's a memory in between. But that's not exactly the same. That's not what you asked. What you asked was basically a feedback loop at this time step. And that particular object is a nightmare to train. Alright, so let's try to make this slightly more formal. Neural network is probably one of the most robust approaches for approximating functions. What functions? You could have discrete functions, in other words, classifiers. You could have real valued functions, in other words, regressors. You could have vector valued functions, which are also basically regression. And today, it's one of the best ways of, one of the best general purpose classifiers if you are in the supervised setting. Remember when I introduced what's it called, ensembles, and I said random forests are the best black box classifiers if you have no other information. That was actually, that statement is from a 2007-ish paper which did a survey of a large collection of data sets. It turns out random forests are still among the best classifiers if you have a smallish feature representation. Now I say smallish, that's not a mathematically concrete statement. It's like the paper recommended if you have fewer than 300 features, you consider random forest. If you have more than 300 features, it turns out that today in large problems that involve very difficult tasks, typically tasks involving human cognition and sensory data, neural networks driven by the backpropagation algorithm is probably the best. It gives you the best results across all methods. So this includes tasks like recognizing characters that are written by the hand, or speech recognition. Microsoft in 2011 produced a speech recognition system that was simply amazing. And today that idea drives all our speech recognition systems that we have. Object recognition in images. You have a photograph, you should tell me whether it's a cat or a chair. nothing comes close to neural networks in this. It's starting to make headway into natural language processing as well. So, I don't think it's fair to have a lecture on neural networks without talking about biological neurons. So here's the one token slide. This is nowhere close to my area of expertise, but I just wanted to bring it up. By the way, this is a this picture here is a drawing of the very first brain cell, or rather, the first drawing of a brain cell. It's actually from a pigeon brain by Santiago Ramon A. Cajal, and this is older than most of us. I'm not going to talk about biological neurons much. I just want to point out that a biological neuron is basically the building block of a nervous system. It consists of very coarsely, it consists of things called dendrites, which you can think of as wires that connect them to other neurons that bring in input into the neuron. And it consists of something called an axon that you can think of as the part of the cell that produces the output, possibly to another neuron. The reason I brought this up is, very often you will see in the news, in papers, in a lot of venues, how artificial neurons are inspired by biology. This is a very loose loose usage of the word inspire. There are so many fundamental differences that artificial neurons could be called a caricature of biological neurons. These just happen to be two things that have the same name. Don't take the similarity too seriously, especially don't fall for media hype. So let's talk about artificial neurons. As I said, they are mathematical functions that very loosely mimic a biological neuron. So, what's a neuron? A neuron is a function that gets an input, typically a vector, and as always we are using the symbol X to denote vectors, the input vectors, and it produces an output, a single output. It takes in a vector of inputs and produces a single output. The way it produces the output is, it first takes a dot product of this vector with some weights, and these weights are associated with that neuron, and actually not possibly, always adds a bias, and then converts this dot product using a nonlinear function called an activation function. So it applies this activation function to the dot product, and the output is produced as the activation applied to the dot product. So in some sense, this should not be a shock to you at all. We've been doing this all the time with one-layer networks. We had this input vector here and a bias, so let me include that as part of the vector. And this part of it is simply the dot product. These wires are associated with the weights. When x1 goes through the wire 1, it gets multiplied by w1. Yes?
How do you choose an activation?
Good question. That's literally my next slide. Just to complete the point, you take the dot product, and so far what have we been doing? We have been taking the dot product and thresholding it. If the dot product plus bias is more than 0, the output is 1, otherwise the output is -1. So the activation function here is called the threshold activation. That's just one of the possible activations. We've already seen another one, by the way. What did we see in the last lecture? The sigmoid, right? So there are many activation functions possible. In fact, there's an entire zoo of activation functions if you go to the Wikipedia page. I've listed a few of them. I just want to mention a few honorable ones, or give a few honorable mentions. The one activation function simply takes the input, which is the dot product, and returns it without changing it, the identity function. And that gives you what's called a linear neuron, a linear unit. We've already seen the threshold unit, which takes the activation function and takes the sign of it. Another one is the sigmoid. We've already seen the sigmoid. It applies this function here. This is sigma of z. Another activation function that's seeing some amount of popularity these days, because it's leading to a lot of state-of-the-art results, is called the rectified linear unit, or the ReLU. The rectified linear unit takes the input dot product. If the dot product is more than 0, it returns it without changing. That's this part of the matrix. If dot product is less than 0, if the dot product is negative, it clamps it to 0. So every activation function you can has a picture. The identity function is just this. The sign is this. The sigmoid looks like this. The ReLU looks like it's 0 here and 1 here. And another one which shows up quite a bit in the literature is the tan h function, which is simply a scaled and shifted sigmoid. Okay? These are just a few popular ones. There are many, many more that are out there, even in publications, being employed. So you can have sinusoidal functions, you can have the sinc function, you can have Gaussians, you can have polynomials, stochastic activations, and so on. Question?
Is there a good reason why these ones are popular, or is it just they seem to work well?
So there are some good reasons, but it's not too many. So I'll give you some good reasons. A two-layer network with sigmoid activation functions can approximate any function. A two-layer network with with threshold activation functions can exactly model any Boolean function. The rectified linear unit shows up because the rectified linear unit has a very interesting lineage. It was invented, it started getting used because as an answer to an optimization concern. And it just so happened that magically using this activation function seemed to improve accuracy. It led to a lot of other interesting properties, and in some sense we still don't know exactly why it works. For example, one hypothesis which actually my student came up with last year was that the rectified linear unit actually simulates a collection of rectified linear units, simulates a much larger collection of thresholds, which in some sense gives you a more difficult, a more expressive hypothesis space for free. Again, it's still an open question. Some of them end up being the usual reason for why we use these functions. They help optimization. So, and the other one is they are kind of these are all simple functions, so they are easy beasts to tame. You can make it more complicated, but again, learning becomes more difficult. Other questions? So, to answer your question, how do you choose an activation function? The answer, and this is going to be something a word that I'll keep using throughout the lecture, cross-validation. You try out a bunch of them and you do cross-validation. Alright, so given this, we have all the tools that we need to define a neural network. Formally, a neural network is a function that converts inputs into outputs. The inputs are usually vectors, the outputs can be either booleans, they can be real numbers or vectors. And the function is completely specified in the form of a directed acyclic graph, something like this. Here I didn't want to draw all the arrows, so all the arrows point upward, on the edges. So the nodes in this directed acyclic graph are the neurons. And the edges correspond to the inputs and outputs of these neurons, and each edge is associated with a weight. Formally, this collection of the nodes, the edges, the connectivity, and the activation function of all of these neurons, plus the weights, completely specify the neural network. The first three of these things, that is the nodes, the edges, and the activation functions, are usually called the architecture of the network. And it's typically predefined, and it's part of, coming up with a good architecture is often part of this sort of design exploration in creating neural networks. It's loosely an art, except that as you do more of it, you kind of get a hang of it. But once you fix the architecture, the only thing that remains to be specified in order to define the neural network are the edge weights. And that's what's learned from the data. That's what we've been doing with SVMs as well, right? We've been learning edge weights for the SVM as well. Questions about the definition of the network? Okay, so
I've got one actually.
yes.
When you're specifying all this, can you pick multiple activation
Yes,
functions?
you can. Absolutely. In fact, that very frequently happens. You can. So I interrupted your question because I knew what you're asking. Can you have different activation functions in different neurons in the network? Yes. And typically, for example, let's say that you're building a classifier. If you're building a binary classifier, the top neuron is fixed. It's a threshold. Doesn't stop you from using sigmoids internally, right? We'll look at an example where we are building a regressor with the top neuron being the identity or the linear unit, and things in the inside being sigmoids. There's nothing wrong with that. Yes.
But they keep the same activation function across a given layer, or they mix and match inside?
Conventionally that happens, but nothing stops you from doing otherwise. At some level, this ends up becoming a beast that you want to tame by applying these kinds of symmetric arguments. If you allow arbitrary freedom, then imagine the nightmare that cross-validation will be. So, there's nothing that stops you from doing it, but it's rare to see it. Alright, so as you know, I like history a lot, so let me give you a very brief caricature of the history of this style of classifiers. These are probably among the oldest classifiers in machine learning. It dates back to a time before the phrase machine learning was ever employed. 1943 saw McLuhan and Pitts develop what is now called the linear threshold unit. And they were not the first people to do it, but they actually showed that the linear threshold unit can simulate or compute logic functions. In 1949, Hebb proposed a rule that's now called Hebbian learning, which kind of has some biological plausibility. 1950s, of course, you know that Rosenblatt came up with perceptron, and you know all about the perceptrons. I'm not going to talk about that. And 1969, Minsky and Papert wrote a book called Perceptrons, which basically killed perceptrons. They analyzed the single layer threshold unit, a single threshold unit from the geometric perspective, and pointed out that they can't represent all functions. Of course, you know that. They are linear functions, they can only represent linearly separable functions, but Minsky and Papert's book kind of formalized this from the geometric point of view. That kind of put a damper on neural network research for a while. Again, in the 80s, things picked up from various different angles. In particular, one big development that happened was this idea of what is now called the convolutional neural network by Fukushima, Yann LeCun, and others. And this was probably the one instance where the artificial neural networks very closely mimicked biology. The convolutional neural network, the first one, was actually designed based on experiments on a mammalian visual cortex. Another big thing that came up in the 80s was what we now call the backpropagation algorithm. The idea existed for a long time, but it was in the 80s that it started becoming popular. And around mid-2000s to now, something changed. We got more data because the internet exploded. Moore's law finally started giving us helping machine learning, in the sense that we could now train massive networks and do the training for a long time. We could train these networks with a lot of data. Basically, we could scale things up, and suddenly things that looked impossible are now doable. We can start dreaming about self-driving cars. This is an extreme caricature. You can go to Jürgen Schmidhuber's his perspective on the overview of this, which pulls in a lot more sources and gives citations if you're interested. There's a link at the bottom. Alright, so as with all hypothesis classes, the one question that you should always ask when you see a new hypothesis class is, what functions do these things express? A single neuron with a threshold activation is the familiar linear classifier. And we know what linear classifiers do. They take the space, slice it into two, and call one side positive and the other side negative. That's basically the only kinds of functions they can represent, functions that fit into that template. If you add another layer with only threshold networks, then you can represent closed objects. You can represent convex objects, polygons in general. The way to kind of very loosely prove this, every line here is a threshold network. That's the hidden layer. And each of them says, this one says this is positive, this one says this is positive, and so on. And the top layer basically looks at the outputs of each of these threshold networks and says the output is positive if all of them say positive. So it's basically a conjunction. So there's a conjunction on top of these thresholds. We know that conjunctions are linearly separable, and these thresholds are basically, what they are, linear threshold units. So a two-layer threshold network can represent these kinds of closed polygons. Okay, let's add one more layer. A three-layer neural network can represent unions and intersections of these kinds of polygons. Now, this kind of a shape, you should, both this and the previous one, should be clear to you that you cannot represent this using things like SVMs or logistic regression. So this is the increase in expressivity that we get when we move to when we add depth. Okay? Now, more formally, neural networks are often called universal function approximators because of some results, again, that at least to my knowledge are from the 80s, but it seems like these things should have been from way before. One famous result is that any continuous function can be approximated to arbitrary accuracy with a sigmoid network, or with a neural network that has the linear unit at the top and sigmoids in the middle. A two-layer network with sigmoids and a linear unit at the top. Any function can be approximated, not exactly, but can be approximated to arbitrary accuracy. And what is even more interesting is this result from the early 90s that says this approximation error is largely, with some caveat, it's largely independent of the choice of this activation function, which means that you can kind of use whatever activation function you want. Again, there are some caveats, and this was a definition insensitive in a particular definition, so take that with some salt and maybe read that paper if you're interested. It's actually not very hard to prove that a two-layer threshold network with over Boolean inputs can represent any Boolean function. And an exercise to you is to try to prove it. The way to think about it is, can you simulate conjunctive normal form using a two-layer threshold network? You can do AND, you can do OR. So you should be able to do conjunctive normal forms. Since I know some of you are, at least some of you are thinking about, okay, what about the VC dimension? For threshold networks, we know some results, and this is still not, these things are not easy to prove actually. For a threshold network with, if you have a neural network, arbitrary depth with only threshold activations, and if you have E, let's say the edges are all called E, the set of edges is E, then the VC dimension of such a network is the number of edges times log of the number of edges. Which kind of makes sense if you think about, say, for example, the perceptron. The VC dimension of the the linear threshold unit is the number of inputs. There's a log term there which I'm not sure how it came in. Is the dimensionality. The VC dimension of a linear threshold unit in D dimensions is D plus 1. In the same ballpark. On the other hand, if you have sigmoids, this gets much harder to prove. We just, to my knowledge, all I know is we have a range. If you have nodes V and edges E, then the VC dimension is more than the number of edges squared, and it's less than the number of edges squared times the number of vertices squared. So you have an upper bound and a lower bound, but to my knowledge, I don't know if there's an exact answer. Questions about any of these expressiveness and sample complexity bounds? Yes?
So when you're saying that we can make any of these functions out of sigmoids or other things, this makes me think to Fourier transforms and Laplace transforms and Chebyshev transforms. Are we saying that those functions we could write those as a neural network rather than just as mathematical transformations.
In theory, yes. All of these theorems come with a footnote that says it's possible that you might require a massive, possibly exponential number of hidden neurons. So these are results that are only existence statements.
Okay.
Does not say anything about the size of the network. So in particular, the middle statement here about threshold networks expressing any Boolean function, it's very easy to come up with Boolean functions that will require an exponential number of hidden units. So there are caveats.
Okay.
So I had a question earlier and you asked me to wait till the.
Okay.
Yeah. So the question was, for an SVM using kernels, where you can have infinite dimensions, and theoretically everything should be linearly separable.
Right.
Versus a neural network where, in the SVM case, you have you have a convex function and you can find.
It's convex in the high dimensional thing.
Right.
Yes.
Whereas a neural network
Is not convex.
Right. So how is it better?
How is it better?
Because you can only find a local.
So this is almost a philosophical question. I'll tell you why. For the longest time, machine learning research obsessed about convex optimization. With good reason, because we know how to handle convex optimization. But what has happened is empirically, it turns out, let's look at a possible landscape for optimization. I want to get to the descent, do gradient descent, and let's say I have this kind of a function. It's not convex clearly. I have two minima. I can either get here or I can get here. Oh, it's gone. I have two minima. I should learn how to get the thing to stay. Anyway, now if you are a purist, you'll say, you know what? I want to get to the one that's lower. Makes sense. You believe that your loss genuinely reflects some notion of error, and you want to get to the lower loss function, the lower loss value, which is all good, but it turns out there's so much noise in the system, and there's so much slip between the loss that you've written down because you know how to solve it, and the actual accuracy, the error that is you care about, that it no longer matters if you get to these kinds of going to one local minimum or another seems not to matter. Now, take everything I said just now with a pinch of salt. All of this is empirically it has been validated on a bunch of data sets, but we do not have good enough theory. So, from the optimization point of view, you're perfectly right. If you have kernels, you still have a convex problem, possibly a very, very high dimensional convex problem, but you still have a convex problem, and the problem is solvable and it's easy. On the other hand, here, learning is actually ridiculously easy to implement in the neural network, and you get to search over the space of functions and get somewhat finer grained control. There seems to be, in some sense, this divergence in ideas between kernels and multi-layer neural networks. Both of them are nonlinear classifiers, and one of them seems to be better than the other, and it's not clear why. There's some ongoing work that's trying to unify these things, that says that, it turns out, for example, that if you use sinusoidal activation functions, you can approximate any shift invariant kernel, which is a kind of a kernel. So, there seems to be some research, it's a hot topic of research, this kind of unifying these two ideas. From the learning point of view, even though the kernels give you formal guarantees, they are actually much more difficult to train computationally. Neural networks don't give you any formal guarantees, but they seem to be much easier to train and work well enough. In fact, better than well enough, they work extremely well. So, open question. Alright, so, another exercise for you is, if you have only linear units in a network, if all the units in your network are all linear, then you should be able to prove that adding depth does not make a difference. You might as well just have one layer. This is an argument that requires you to kind of exercise your linear algebra chops. Alright, so let's look at an example of a neural network. This is the example that we'll be looking at for the rest of this lecture. Here's a two-layer network. It has inputs that are called, I'm going to use the convention X for inputs. The Y, as always, as we've seen so far, the Y is the output. And the hidden layer, there's one hidden layer, and it's, I'm calling them the neurons in that layer, Z. Okay? There is a bias feature, and typically in the neural network universe, it's important to actually explicitly write down the bias because it seems like it's very convenient to forget it. So I'll be writing the bias down. So there's a bias feature, Z0 and X0 are basically always 1. This only defines the graph. This does not define the activations and the weights. In terms of activations, I'm going to, in this case, let's say the network has two sigmoid activations in the middle. V1 and V2 are actually sigmoidal units. And the output unit is a linear unit. So what we have here is regression. The input is some vector and the output produces a number. It's a regression. This network does not linear but non-linear regression. And every edge has weights, and because I'll be using these things quite a bit, I'm going to establish a naming convention here. Every weight is going to have a subscript and a superscript. The subscript says what is the input, and okay, let's just use this one. The subscript here says that this neuron goes from this edge, takes the output from the second unit to the second unit, that's 2, 2, in the hidden layer. So the superscript here says what's the layer that this edge belongs to. The input, which layer is this edge going into. So W01O means this edge connects the zeroth neuron to the first neuron in the output layer. There's only one neuron in the output layer, so it doesn't matter. I could have just dropped the second element of the subscript for this one. So all I have done so far is just give names to things. I have described the neural network and I have named the nodes. I have told you what activation functions are in play here. This is just completely made up. I made this up entirely. This has got nothing to do with any sort of application or anything. The hidden neurons are all sigmoids and the output is a linear one. So at this point, if I knew the values of the W's, I should be able to make predictions, right? Because everything else is done. How does the prediction work? The way the neural network predicts, it's also called the forward pass. So for the prediction problem, the input's some vector, and what you do is you go from bottom up, and every time you encounter a neuron, you compute whatever it does. You basically compute whatever the neuron computes. So for example, let's actually work this out. You have Z1, which is a sigmoid activation function. Sigmoid of what? The dot product of the inputs and the weights. So the output of Z1 will be a number between 0 and 1 because it's the output of a sigmoid. Z2 is another sigmoid, which is the output, the sigmoid of some other weight, the dot product of some other weights and the same input. And now we've computed the hidden layer units completely, we can move on ahead. The output turns out a linear activation, which means there is transforming the dot product. It's just the dot product of the weights of the output layer times the input to the output layer. What's the input to the output layer? The input to the output layer is the current state of the hidden layer. And this gives us the output of the neural network. This is how the neural network makes a prediction. And this is generally true for, this is a two-layer neural network. This is the way it works for all neural networks. Questions? Yes?
So why don't you have sigmoid function of outputs?
Oh, I just decided to, no reason. I'm the designer and I made a choice. And really no reason. Let's just say that I wanted a regression. Sigmoid gives you only numbers between 0 and 1. In this case, I wanted real numbers. Surplus. This is a cartoon example that will help us, derive a backpropagation. Yes.
So we've been writing all of our output layers as having a single output. Would you ever have it that has
Absolutely.
more than one?
Typically, so if you want to do multi-class classification, for example, a cheap way of doing, an easy way of doing multi-class classification is to have as many threshold units at the top as you have classes, for example. Or you can have as many sigmoids at the top as you have classes and pick the label of the highest scoring class. Sometimes you might want to produce vector valued outputs. Why would you want to produce vector valued outputs? Maybe because you want to actually produce a representation of the inputs. You don't really care about predicting anything. So yes.
So can we do something like if we need 4 different classes, we have 2 neurons at the output?
You
and
could
one
do some
big thing?
fancy encodings and stuff, but typically the usual way of doing it is one part. Namely, every label gets a different thing. And that's often better because if you do any encoding, you are implicitly making assumptions that some labels are closer to others. And you don't want to. Maybe not. Maybe you do, maybe you don't. It's all notice how everything is up for grabs here. Alright, so what we've seen so far is what are neural networks, about their structure, about the formal definition and their expressiveness. So in some sense, the only thing, so we've seen how neural networks make prediction. Anytime you see a new hypothesis class, you should ask yourself 2 questions. How do you predict that hypothesis class and how do you learn? We just saw how it predicts. So the only thing left to completely define this hypothesis class is how it learns. And this is the famous backpropagation algorithm. Let's set up the learning problem before getting into backpropagation. Typically, the way that the training works is you're given a network architecture. Namely, you're given the shape of the network. You're given all the nodes, all the neurons, their connectivity, and the activations on all the neurons. So you have the entire neural network except for the weights. And you have a data set instead of the weights. And the data set consists, as always, of examples. And we just use the notation we've been using so far, x's and y's. X's are vectors, d-dimensional vectors, and y's could be booleans, it could be real numbers, it could be more complex objects. But for now, let's just say that these are either numbers or booleans. Our goal now is to use this data set to figure out what the weights on the edges are. That's the learning problem. Now, keep in mind that even though you see all this kind of, there are so many moving parts here, at the end of it, mathematically, a neural network is just a function that takes some input, x, and makes a prediction. I'm going to call it y hat on this slide, but very quickly I'll drop that. And for a fixed architecture, the only thing that is allowed to change is the weight, all the weights of the network. And every function in this hypothesis class is uniquely defined by an assignment to the weights, right? So the learning problem is just figuring out what the weights are. And this is where everything that we saw in the semester kind of converges. Remember, we saw that learning can be framed in general without loss of generality. You can write down learning as minimizing empirical loss. All you need to write down empirical loss minimization is a function that takes inputs and produces an output, and the function has to be parameterized by whatever you want to learn. So we have a function that's called this, I'm going to call it neural network, NN. This function is completely defined by the choice of W. So given a data set, we can learn the weights by minimizing the total or average loss on the data set. Perhaps maybe with a regularizer, but I'm not showing a regularizer here because it just makes the slides messy. This idea is not new. It worked for logistic regression in the last lecture. It worked for support vector machines. You hopefully were able to prove that perceptron is also minimizing, the perceptron algorithm is exactly loss minimization. We saw how regression can be written as loss minimization. The only thing that changes across these four things is a different loss function. All of them are linear models. If it works for linear models, it works for nonlinear models as well. So, in terms of our running example, remember we had the neural network and we are able to make a prediction. The prediction is inside this dotted box. That's the forward pass. Let's say you see this input, you make a prediction. We are calling it Y now. And at that point, you also have the true label for this input. Let's call it Y star. Now, I can always write down some notion of loss. This is the regression problem. A natural choice of loss for regression is the squared loss. So we can say the penalty that this set of weights makes has to pay for making a prediction Y is the square difference between Y and Y star. There's a half there, but that's just for making calculus easy, or actually making so that we don't have to carry around a constant. But the penalty that the classifier pays for mispredicting Y star as Y is the difference between them. And what is Y? Y is literally just the output of the neural network. It's run the forward pass, you get a prediction, and you can compute this loss. So this is an example of a loss. We've seen others. We've seen the Hinch loss. We've seen the logistic loss. If you want to do classification, you can use one of those. So in some sense, all the pieces are in place. So all we have to do is solve this optimization problem. How do we solve this optimization problem? How did you solve this optimization problem the last time you saw it?
Stochastic gradient descent.
Stochastic gradient descent has become, in some sense, there are many ways of course, but stochastic gradient descent has become the de facto recipe for solving these kinds of optimization problems. Let's just look at SGD again. We've seen this before. You have an objective that you want to minimize. In this case, the objective is parameterized by this, is defined in terms of this neural network. You're given a data set. You have M examples, let's just call it S, the data set. You initialize your neural network, parameters, W to something, and we'll get to that later. And you run multiple epochs on the data. And you, after running these epochs, whatever remains, you return. Inside each epoch, you shuffle the training set. This must be awfully familiar because you've implemented this at least twice. You shuffle the training set and you iterate over the examples. You pretend that the current example is the entire training set, and you compute the gradient of the loss function with respect to the weights at that point. Now you have a gradient. The gradient points in the direction of the steepest ascent. You want to descend, so you go in the opposite direction. So you take a step, you reduce the weights by the gradient. It's exactly what we've done so far. Couple of things to keep in mind. The learning rate, gamma t, is the step size in this gradient descent, and there are many possibilities. A somewhat more important concern is the objective L is not convex because the neural network is not necessarily a convex function. So there are no guarantees, which means that initialization becomes important, and there are many tricks for initialization that exist out there. So, any questions about this? This must look awfully familiar. We've seen this at least 3 times so far. Any questions? Okay, I have a question. Have you solved everything? Can you go out there and implement this? Say for that network that I just gave you. Is there anything missing? You have half a hand raised up, and you have as well. So you've spoken before, so you can go.
Maybe we should do an update. Do we have any update? Like, when we need to update W?
Oh, you update W all the time. You're doing a gradient descent, so you always update.
Gradient.
Like who's? Yeah. So can you repeat that?
I think the gradient.
So everything is solved. You're right. Everything is solved except Now the gradient it's not clear how to compute the gradient of this loss function. If you knew what this gradient was, you could literally just implement this algorithm in whatever Python or whatever language you want. If only you knew a way to compute the gradient. I'm glad you asked that question because I'll give you a way to compute the gradient of the loss function. But let's just think about what this means. We want to compute this the gradient of the loss function with respect to the W weights. It's a differentiable function. Typically neural networks are differentiable functions unless you have a threshold activation. At this point, it's not differentiable, which is why thresholds are not used a lot. As long as it's differentiable or sub-differentiable like the hinge loss, you can find a subgradient and you can do stochastic subgradient descent. Whether the function is, whether you use the subgradients or gradients is entirely decided by the loss function and the activations. Sometimes this was easy, believe it or not, it might have been a pain for you, but it's actually easy for logistic regression. It's easy for support vector machines. In fact, your homework question is asking you to compute the gradient exactly to solve this problem for logistic regression. So that's easy. But the neural network is a beast. It's a really complex function. How do you find the subgradient? Just to give you an example of how complicated it can get, a recent paper which is, I think at least as of 3 months ago, was the state of the art for an object detection task, had 150 layers of various kinds of activation functions, each one carefully chosen and lovingly placed. So how do you compute the gradient of this really massive function? And let's say you compute the gradient on paper. Let's say you do all the dirty work, you write down the gradient, and you find it doesn't work, and you have to add one more layer, or you have to take out a layer. At that point, you have to redo the whole thing, right? So, at this point, what you really need is an efficient algorithm that does your calculus for you. A way of doing partial derivatives, computing partial derivatives on the fly, automatically. And that algorithm is called backpropagation. So, just to give you a checkpoint of where we are. If you have a neural network with the entire architecture and the weights, we can make a prediction. That's the forward pass. If you have the true label for a particular input, you can define you can mathematically define the loss function, right? We just defined it as the squared loss. If you are able to take the derivative of the loss function, then you can apply it in stochastic gradient descent. And you have the complete learning algorithm. This is the forward pass. So we know how to do this. This is something that we've looked at through the entire semester. We've seen multiple loss functions. The only thing that's left is how do you take the derivative of the loss function? And the answer to that is we employ the backpropagation algorithm. So before going ahead at this checkpoint, any questions about any of this? So you should be able to at least implement the forward pass, or at least have a mental idea of how to implement the forward pass at this point. Let's get to the backpropagation. So the thing to keep in mind for backpropagation is it repeatedly employs the chain rule for taking derivatives. So let's just remind ourselves what the chain rule is from, I don't know, middle school or something. Let's say you have some x, and the x is converted to y using a function, and y is converted to z using possibly a different function. So z is also a function of x, right? I want to take the derivative, the partial derivative of z with respect to x. Z is not directly a function of x, and the way to do it is we know that z is indirectly a function of x through y, so you take the partial derivative of z with respect to y times the partial derivative of y with respect to x. This is calc 1, hopefully, or 2 or 3, I don't know, one of the calcs. Okay, so this is easy. same thing should go, we can expand this. So let's say your output is not just a function of y, but it's actually a sum of two functions, y1 and y2. And each of them, y1 and y2, are functions of x. Then the partial derivative of, I still want to find the partial derivative of z with respect to x. It's the sum of two things. You find the partial derivative of z with respect to y1 times the partial derivative of z with respect to x plus the partial derivative of z with respect to y2 times the derivative of y2 with respect to x. This is also should not be particularly shocking to you. Is it shocking to you? I see at least two heads nodding, so I'm assuming that represents the class. The same idea can be extended to bigger sums. If your z is the sum over I equals 1 to n of yi, then the partial derivative of z with respect to x is simply, I take the, and I know that each of these yi is a function of this x, then the derivative of z with respect to x is a sum, again, of these products. Take the derivative of z with respect to the yi times the derivative of yi with respect to x. So I'm going, so for y1, for example, I'm going down this path, this path. So it's the product of derivative of z with respect to its input times the derivative of y1 with respect to its input. And this can go down multiple if you have the function more compositions as well. So the tool, in some sense, the only tool that you need to understand backpropagation formally is how do you take their partial derivatives of compositions of functions. If you are able to understand that, it's kind of easy, trivial to derive the backpropagation algorithm. So let's try to derive the backpropagation rule for this particular network. Just to remind you, let's assume that at this point we've already done our forward pass. We have an input, we've done our forward pass, we have calculated y, and we can even write down the loss function. So what we want is to compute the derivative of the loss with respect to all the weights. There are two kinds of weights here in this network. I mean, you can have more in bigger networks. There are some which are associated with the output layer, like these three here, and there are some which are associated with the hidden layer, like I've written only two, but every edge has a weight. I want the derivative of the loss with respect to all these weights. This is just an extension of the idea that we've been looking at all the time, right? We're taking the derivative of the loss with respect to the weight vector. Questions before going ahead? So, how many people have seen backpropagation before, by the way? How many understand it? 1, 2, okay, 3 people. Alright, so I think the only way to actually really get backpropagation is to work out the math. I mean, this is true for all kind of messy algebra. You need to do it yourself. So, but let me walk you through an example. Backpropagation is simply applying the chain rule repeatedly. It's really only two ideas that completely define this algorithm. You apply the chain rule repeatedly, and if you find yourself calculating a partial derivative that you've already done before, you don't recalculate it, you just use the previous answer. The oldest trick in computer science. Instead of computing something, remember it. In this case, we are remembering partial derivatives. Let's see how that works. So let's first consider this weight here, WO01. I want to calculate the partial derivative of the loss function with respect to this weight. Let me apply the chain rule. The loss function, how did this happen? Oh, that's so cool, I can zoom in. The loss function is just a function of, I've written the functions that we have that are relevant at the top. The loss function is not a function of this thing that we care about. It's a function of the y. Y star is a constant, y star is fixed. The loss at this point is just a function of the y. It just so happens the y is a function of the thing that we care about, WO01. So I want to calculate the derivative of L with respect to this weight here, but it's indirectly a function of, L is indirectly a function of that weight through y. So You apply that, we use partial derivatives. We write down the derivative of L with respect to the weight as its derivative with respect to y times the derivative of y with respect to WO01. The derivative of L with respect to y is just easy. This is your function here at the top. The derivative is just y minus y star. There's nothing complicated there. And also the derivative of y with respect to the weight is also easy. It's just the number 1. So we've already calculated the update for this weight here. It is the product of these two things. Questions? Okay. Let's try one more. I want to calculate the partial derivative of L with respect to this weight, WO11. What do you do? L is not a function of WO11. It's just a function of y. So you apply the chain rule again. L is a function of y is a function of the weight. So the partial derivative is just the product of these two partial derivatives. But the derivative of L with respect to y again is the same thing. It's the derivative of L with respect to that function with respect to y, it's y minus y star, and the derivative of y with respect to this number, this weight is the value of z1. How do you know what z1? We've already done a forward pass. We've calculated all the z's, right? So we have the z1. So you do the back propagation after doing the forward pass. Now notice something interesting here. This derivative of L with respect to y is something that we just calculated for the previous one. There's no reason for me to redo this math. If I've already done it before, I can just remember it. Which means we save one step of computation. In this case it's just one, but as your network becomes deeper, the savings becomes a lot more. Questions? Yeah, but the z1 is, as far as this point, at this point, it's just this number here. We've already calculated it.
Oh, for that particular...
For that, we are calculating the derivative for that particular example. Remember, this is situated in stochastic gradient descent. We have a particular example. We have run the forward pass, which means you have calculated all the states of these neurons. And now we want to go back and calculate derivatives with respect to the weights. And one of the reasons backpropagation is fairly daunting is because of this glut of symbols. There are so many, the notation is often awful, mine included, and I think unavoidable. Anyway, so the most important thing to note here, this is the first place we are encountering this idea that some of these partial derivatives need not be computed. Because this quantity here was already calculated in the previous step for when we calculated the partial derivative with respect to the other weight. So you remember it and you save a little bit of computation. Okay, that was with respect to the outputs. In the time that's left, I'm going to try to get to the partial derivatives with respect to the hidden layer weights. The idea is the same. So again, you have a neural network, we've done the forward pass, we get the entire set of states of neurons, we are able to write down the loss function, and I want to calculate the partial derivative of the loss function with respect to this weight here. How do you do it? It's again repeated application of the chain rule. L at this point, all we know about L is that it's a function of y. We don't know anything else. The only variable in L at this point is y. So what do? You want to calculate the partial derivative of L with respect to y, with respect to the weight, but L is only a function of y, so you apply the chain rule. You get dl by dy times dy by the weight that we care about. What is y? It turns out y was produced as a dot product of these weights with these features. That's right here. The weight that we care about is still not in the y. Is still not on the right hand side of y. We care about W22H, there's no W22H here. So what do? Let's just substitute this for now. I'm kind of taking a shortcut here just to make the point. Let's substitute and apply this derivative to the summation. This is a constant with respect to W22, so this goes away. And turns out that Z1 is also not a function of W22. Z1 has nothing to do with W22. So that also goes away, goes to 0, and we are left with the partial derivative of y, of L with respect to y times W21 times the derivative of Z2 with respect to W22. Now at this point, notice that the notation is getting rather unwieldy. But there's a reason why I'm doing this. Z2 is now the sigmoid. The sigmoid applied to what? Sigmoid applied to a dot product. Let's just make our lives a little bit easier by introducing more notation. Let's call the dot product S. So Z2 is sigma of S, where S is that sum. So I can write this, again the chain rule applies. I only want to write down what this function is. Z2 is a function of S, and S is a function of W22. So I can write down the partial derivative of L with respect to W22 as the product that we've been carrying along so far times the derivative of Z2 with respect to S times the derivative of S with respect to W22. If this is tedious, it's deliberate. What we have done so far is we've written down the derivative of L with respect to the weight so far as this product of partial derivatives. Notice that the product basically goes along the path that goes from the output, actually the loss is here, to the weight that we care about. So there is loss with respect to y with respect to this weight, this with respect to Z2, and this with respect to this. So we are basically tracing the path back from the loss all the way down to the weight that we care about. And each of these things is easy actually. We've already computed the partial derivative of L with respect to y. The partial derivative of Z2 with respect to the sum is Z2 times 1 minus Z2. I'm not going to tell you why. I derived it in the last lecture, so you should. Z2 is just a sigmoid, so it works. And finally, we are getting to the partial derivative of S with respect to the weight that we care about is x2, because only this term survives. The important thing is, many of these things are actually going to be already pre-computed for you at some of the previous steps. For example, you never have to compute this more than once. So a lot of caching happens. So putting all these ideas together gives us the backpropagation algorithm. We are going from the top to the bottom. You repeatedly apply the chain rule. You first perform the forward pass, and then once that's done, you compute the loss, and then you keep applying the chain rule, going back. And every time you compute a partial derivative, you remember it, so that you don't have to recompute it. This memoization of partial derivatives lets you efficiently compute the entire gradient of the function. At that point, you can plug it into your SGD, and you have, in some sense, a way of mechanizing learning. So this is the last thing I want to say today. The backpropagation algorithm gives you a gradient that will be used in gradient descent. We already know how to use gradient descent for solving, for, in some sense, defining a learning algorithm. Gradient descent gives you a recipe for writing down learning algorithms. Backpropagation is a recipe for computing the gradients. So, in some sense, what we have done is we have automated the problem of writing down learning algorithms. We can now create learning algorithms by just defining the network and a loss function. It's a recursive algorithm, and this process of backpropagation is so mechanical that you can actually write software that does your calculus for you. Most standard libraries today, TensorFlow and Theano and such things, do this automatic differentiation using backpropagation, which is actually one of the reasons why we are able to develop these massive networks and explore the search space. Because you don't have to do what I just did by hand all the time. Alright, I'll stop right now. If there are any questions, I'll take them. Maybe since we are out of time, you can meet me after class. Otherwise, we'll continue in the next lecture. I'll finish up this neural network and talk about nearest neighbors.